This would correspond to the first problem on the 170320 document. We have a bunch of wrestlers, different weights, and they weigh in. And we get this distribution of the weights. We have one with a weight of 123, 3 with 124, 6 with 125, etc. So we set this up as a frequency distribution where we indicate the number of times each weight occurs. Okay, well, we want to add up all these weights. Now, we don't just add up these numbers. We have to multiply each weight by the number of times it occurs to see what we would get from that weight if we listed all the weights. If we listed the weight of every individual, we would list 124 3 times, wouldn't we? We'd list 126 10 times. Okay, so instead of listing them all and adding them all up in that column, we make it a little easier. So since there are 3 at 124, we multiply 124 by 3. 6 at 125, we multiply 6 by 125. We get these numbers over here. So let's see, these are our numbers x. X stands for the thing that we're observing, okay, the quantity that we observe. It's a variable quantity. F stands for the number of times x occurs. And x times f is what we get when we do what I just said, multiply each weight by the number of times it occurs. Okay, so if we add up all the frequencies, we find that these add up to 24, meaning there are 24 people. Well, that we indicate by a summation of x. The sum of all our frequencies is 24, okay? And we call that n. That's how many people we have. That's our n for this distribution. Now, we add up all our x times f's, and we get 3014. And then we calculate the mean. Okay, x bar is our mean, and that's what we get if we add up all the x times f's, sum of all the x times f's, which is 3014, divided by the sum of the f's, or by, we often call this n, so we could, instead of sum of f, we could use n here if we wanted. In any case, that's 3014 divided by 24, about 125.6. Okay, that gives us a mean for our distribution. Now, if we do a histogram of our distribution, it looks something like this, with 123 here and 128 here. You would make that histogram because it's the first thing you're asked to do in that problem. What's our balancing point on this distribution? Well, people say, well, it looks like it's about here. Now, I didn't draw the distribution perfectly. There are a few more over on this side than there are on this side, so the mean is going to be a little bit to the left of the middle. Probably not that far. One person who generally does things right got a mean that was way over here. Well, obviously, if the person has that histogram and the mean tells him that the balancing point is over here, because that's what the mean is, it would be the balancing point. Obviously, he punched the wrong button or did something wrong. He redid it and got what he should have. Okay, so you want to have a picture of the histogram, and you want to check that against the mean that you get to see that your mean is reasonable. In any case, there we have our mean. Now, we also add columns for the deviation, the squared deviation, frequency times squared deviation, because the squared deviation, okay, the deviation for 124 is 1.6, meaning that 124 differs from 125.6 by an absolute value of 1.6. There are 3 of those, okay? So we can square that deviation, get to 2.56. If we're wanting to add up all our squared deviations, we're going to have 3 of these. So we'd have to multiply 3 by the 2.56, which is a squared deviation of 124. Okay, that would give us the 7.68 we see here. So, calculating a standard deviation, we calculate all our deviations, which is just how far each x value is from the mean, the squared deviations, and then multiply each squared deviation by how many times it occurs, and then we add those up and we get the total of our frequency times squared deviation. In this case, that's about 30. Okay, then we calculate the mean of our squared deviation, which, and right now, there's a little caveat that we'll talk about here, but the mean of our squared deviation, we divide our total of our squared deviations, 30 in this case, by the sum of f, or by n, which is the same as the sum of f. That would be 24. And we get 1.25. Then our standard deviation is the square root of the mean of our squared deviations, which is square root of the add up all the f's and divide by the sum of all the f's, or by n, and we get this result. Because, why? Because we define the standard deviation as the square root of the mean of the squared deviations. So, what do we have to do? We first have to figure our deviations, which we did here. We square our deviations here. We want the mean of the squared deviations, so we'd better count every squared deviation once for every time that particular instance occurs. Then we add all those up and divide by how many people there are in this case. Now, one adjustment: if n is less than 30, and n is our sum of f, we could call that n if we wanted to. If n is less than 30, then by the so-called mean of our squared deviation, and the thing we're actually going to use, is the sum of all your frequencies, all frequency times the sum of all your squared deviations, divided by n minus 1. 24 minus 1 instead of 24. And that gives us a standard deviation that's a little bit higher than this one. Doesn't make a lot of difference. And by the time we get to n equals 30, it doesn't usually make any significant difference. So we stop dividing by one less. It's not quite that simple, and the reasons for that go kind of deep, so we don't want to talk about it. The other thing I'll do, just to clarify a little bit, instead of sum of f, just to be really clear about this, I could use n, right? And it would all mean the same thing. And here would be n minus 1.